A light year sounds like a unit of time, but it is really a measure of distance so huge that the human mind almost refuses to hold it. It is the kind of distance that turns nearby stars into remote islands, makes our fastest spacecraft look almost frozen, and reveals that when you look into the night sky, you are not just looking far away. You are looking back in time. And that matters more than it first seems, because once you truly understand what a light year means, space stops feeling like a beautiful backdrop and starts feeling like a place with real depth, real delay, and almost unimaginable scale. By the end of this, a phrase you have heard 100 times will mean something vivid, physical, and slightly unsettling. The universe will feel larger, stranger, and far more real. And if you enjoy space videos that try to make these huge ideas feel clear and alive, take a second to like the video and subscribe. It really does help, and only if this is your kind of thing. And in the comments, tell me where you are watching from, and answer this. If you could instantly visit any star system within 10 light years of Earth, which one would you choose? Now, with that in mind, let us step away from the familiar ground under our feet and out into the dark, where distance stops behaving like intuition says it should. Imagine the night sky without the comforting illusion that everything up there is part of one flat ceiling. Imagine every star separated by gulfs so vast that even light, the fastest thing we know, needs years to cross them. Imagine trying to build a map of a universe where distance is measured not in miles or kilometers, but in the travel time of light itself. Why would astronomers use such a strange unit in the first place? How far does light actually travel in a year? If light moves so absurdly fast, what kind of cosmos forces us to think in years just to describe the gap between one star and the next? And what does it really mean that the more distant the universe becomes, the more ancient it appears? To get there, we begin with something familiar. Light is fast, very fast. In everyday life, it feels instantaneous. You flip a switch, and the room brightens. You look at a mountain, and you do not imagine a delay between the mountain and your eyes. The world seems immediate, or cause and perception feel almost identical. But that is only because the world we live in is small, at least by cosmic standards. Light travels at about 299,792 kilometers per second, or about 186,282 miles per second. In 1 second, it can circle Earth more than 7 times. Not in a minute, in 1 second. If you could move that fast, you could leave London, pass over New York, cross the Pacific, race above Antarctica, and still have time left over before the first second was done. Light is so fast that for most of human history, many people assumed it must be instantaneous. That assumption did not survive careful observation. In the 17th century, the Danish astronomer Ole Rømer noticed something odd about the moons of Jupiter. Their eclipses did not occur exactly when expected. They seemed to shift depending on where Earth was in its orbit. When Earth was farther from Jupiter, the events looked delayed. When Earth was closer, they seemed earlier. The moons were not changing their behavior. The light was taking different amounts of time to reach Earth. It was one of the first powerful clues that light had a finite speed. That discovery did not just tell us something about light. It told us something profound about reality. The universe does not deliver information instantly. Every sight is delayed. Every view is historical. The only question is, by how much? For your hand in front of your face, the delay is tiny. For the moon, it is noticeable only if you care about precision. About 1.3 seconds. When you look at the moon, you are seeing it not as it is now, but as it was a little over a second ago. If the sun vanished, and setting aside the much bigger physics problem of gravity for a moment, Earth would continue receiving sunlight for about 8 minutes and 20 seconds. Sunrise itself is already old by the time it reaches you. 8 minutes does not sound like much. A light minute is manageable. A light hour starts to feel more dramatic. A light day is already enormous, but the stars are not light minutes away. They are not even light days away. That is where the light year enters the story. A light year is the distance light travels in 1 year through the vacuum of space. That is all it is. Not time, but distance defined by travel time. You take the fastest speed we know, let it run for an entire year, and the result is 1 light year. The number is ridiculous in the way cosmic numbers often are. In 1 year, light travels about 9.46 trillion kilometers, or about 5.88 trillion miles. If you say that quickly, your mouth can finish the sentence long before your mind catches up. Trillion is one of those words that sounds familiar but behaves like a cliff. It is easy to step onto it verbally, and very hard to look over the edge. So, let us slow that down. 1,000,000 seconds is about 11.5 days. 1,000,000,000 seconds is about 31.5 years. 1,000,000,000,000 seconds is about 31,000 years. That is the kind of gap hidden inside the word trillion. So when we say light travels nearly 6 trillion miles in a year, we are not talking about a very long road trip. We are talking about a scale that already exceeds ordinary imagination. This is why astronomers do not usually describe the distances to stars in kilometers or miles. They could. The math would still work. But the numbers would become so enormous, so quickly, that they would stop helping. Saying Proxima Centauri, the nearest known star to the Sun, is roughly 40 trillion kilometers away, is technically correct. Saying it is about 4.24 light years away tells you something more meaningful. It tells you that even light, moving at the maximum cosmic speed limit, needs more than 4 years to get there. And that one shift changes everything. Because now distance is no longer just quantity. It becomes delay, it becomes history, it becomes a built-in waiting time written into the architecture of space itself. To feel how strange that is, picture a conversation between worlds. If there were someone standing on a planet around Proxima Centauri with a powerful telescope pointed at Earth, what would they see right now? Not tonight as you know it. Not this exact moment. They would see Earth more than 4 years in the past. Every signal, every broadcast, every flash of city light moving outward at the speed of light would still be making that journey. If you sent a message today, and they somehow answered instantly the moment it arrived, you still would not hear back for more than 8 years. A simple exchange of hello and hello back becomes a decade-long event. That is what a light year really means in lived terms. It means that space is so large that even the universe's fastest messenger cannot make it feel immediate. And this is just the nearest star. Our own solar system, which already feels vast on human scales, is tiny compared with the distances between stars. Neptune orbits the Sun at an average distance of about 4.5 billion kilometers. Sunlight takes roughly 4 hours to get there. The Voyager 1 spacecraft, one of the farthest human-made objects from Earth, has been traveling for decades. It moves incredibly fast by our standards, but on the scale of stars, it is almost painfully slow. If Voyager 1 were headed toward Proxima Centauri, and it is not, it would take tens of thousands of years to arrive. Human engineering can fling metal across the solar system. Reaching the stars is a different category of challenge entirely. This is where our instincts begin to fail us. We are used to maps, where continents can be crossed in hours and messages move around the world in less than a blink. We live in a civilization built on shrinking distance. But the cosmos does not care about our convenience. The nearest star beyond the Sun is not another stop on a route, it is an abyss away. And yet the night sky hides this beautifully. Stars look packed together. Constellations seem neat and close, like points pinned to a dark dome. Orion looks like a shape. The Big Dipper looks like a shape. But those are perspective tricks. The stars in a constellation may have nothing to do with one another physically. Some are relatively near. Some are far more distant. We draw lines between them because from one tiny moving platform called Earth, they happen to line up. It is like looking from a highway and seeing distant mountains and nearby trees appear side by side. The sky is full of false neighborhoods. Once you start measuring in light years, that false flatness collapses. Space acquires depth, real depth. A star that seems modestly bright may be nearby and faint, or far away and blazing. A dim red point might be one of our closest neighbors. A brilliant blue-white beacon may be hundreds of light years distant. The sky stops being a pattern and becomes a layered history of emissions from different times and places, all arriving together tonight. That is one of the most remarkable things about astronomy. Most sciences can bring the subject into the lab. Astronomy often cannot. It studies what arrives. Light is the evidence. The night sky is not just scenery. It is a stream of ancient messages. When you see Sirius, the brightest star in Earth's night sky, you are seeing light that left about 8.6 years ago. Arcturus, one of the bright orange stars, sits around 37 light years away. Vega is about 25 light years away. Betelgeuse, the swollen red supergiant in Orion, is hundreds of light years away. Depending on the estimate, often around 500 to 700 light years. So the Betelgeuse you see is not current Betelgeuse. It is historical Betelgeuse. It may still be there, much as we know it, and likely is, but what we know is delayed by centuries. This sometimes produces dramatic misunderstandings in popular science. People hear that a star could have exploded already and think astronomers have no idea what is happening. The truth is subtler. For distant objects, we know only what their light has had a time to tell us. If a star is 600 light years away, then yes, an event that happened there 300 years ago would still be invisible to us. We would still be seeing an older version. That is not ignorance in the ordinary sense, and that is the structure of causality in a finite speed universe. And that finite speed does something extraordinary as distances grow. It turns telescopes into time machines. Not machines that move us through time, of course. Nothing so cinematic. but machines that gather older and older light. Looking farther into space means looking farther into the past. This is not metaphor. It is literally how observation works. The Moon is 1.3 light seconds away. The Sun is a little over 8 light minutes away. Jupiter is tens of light minutes away, depending on where it is in its orbit. Pluto is several light hours away. The nearest stars are light years away. The center of our Milky Way galaxy is around 26,000 light years away. So when astronomers observe that crowded, dust-veiled region, they are seeing it as it was when human civilization looked very different. The Andromeda galaxy, our nearest large galactic neighbor, is about 2.5 million light years away. The light entering a telescope from Andromeda tonight began its journey long before modern humans existed in anything like their present form, and that still barely scratches the scale of the observable universe. There are galaxies so distant that their light has been traveling for billions of years. When space telescopes observe some of the earliest galaxies, they are catching light emitted not long after the first stars and galaxies formed. The James Webb Space Telescope, for example, is designed in part to study this early cosmic era by detecting infrared light from extremely distant objects, much of it stretched by the expansion of the universe. It is not peering into fantasy. It is collecting ancient photons that have crossed an expanding cosmos to reach us. So a light year begins as a simple distance unit, but it quickly becomes more than that. It is a bridge between geometry and time. It tells us where something is and when we are seeing it. Now, there is an important detail here, because this is one of those ideas that sounds simple and then becomes slippery. A light year is based on the speed of light in vacuum, in empty space. Light can move more slowly through materials like water or glass. That does not change the definition. The cosmic speed limit, the one built into relativity, is the speed of light in vacuum. That is the speed used to define the light year. And relativity matters here in another way too. Except, we often casually say that light is the fastest thing in the universe. That is true in a practical sense, but more precisely, the speed of light in vacuum is the maximum speed at which information or causal influence can travel according to our current best theories. That is why the delays are not just inconvenient. They are fundamental. You cannot simply decide to signal faster because the distance is annoying. This has enormous consequences for travel, communication, and our dreams about the stars. Science fiction often makes interstellar journeys feel difficult but manageable, as if the galaxy were an ocean crossed by better ships. In reality, unless some new physics one day changes what seems possible, the distances are savage. A star 4 light years away is close only in a cosmic sense. At speeds achieved by current spacecraft, and that journey is not a mission. It is a civilizational commitment. Suppose you had a craft moving at 60,000 kilometers per hour, which sounds impressive because it is impressive by human standards. At that speed, reaching Proxima Centauri would take many tens of thousands of years. Increase the speed dramatically, and the times become shorter, but still daunting. To cross a single light year in 1 year, you need to move at light speed. And according to relativity, any object with mass cannot be accelerated to light speed. The closer you get, the more energy is required. The problem becomes brutally difficult. That does not mean interstellar travel is impossible in every form anyone has imagined. Scientists and engineers have studied concepts like laser-driven light sails, fusion propulsion, antimatter ideas, generation ships, and other speculative approaches. Some are grounded but far from practical. Some remain deeply uncertain. The point is not that humans will never reach another star. The point is that a light year tells you why the stars have remained, so far a realm of observation rather than visitation. When people hear the term, they often make a very understandable mistake. They imagine a light year as a kind of abstract astronomy word, something that sounds advanced, but mostly functions as jargon. In reality, it is one of the most humanly revealing units in science, because it captures the central fact we keep trying to ignore. The universe is not built on our scale. On Earth, even long distances can become personal. You can drive across a country, fly across an ocean, send a message across the planet instantly, watch a storm from space in real time, or call someone on the other side of the world while making tea. We have engineered ourselves into a feeling of nearness. Space strips that away. If the sun were the size of a large orange, Earth would be a small grain of sand roughly 30 meters away. Neptune would be about a kilometer distant. On that scale, the nearest star would still be thousands of kilometers away. Not the next house, not the next city, another continent. Our solar system is mostly empty. Interstellar space makes that emptiness look crowded. This is one reason the phrase astronomical distance exists in ordinary language. It is not poetic exaggeration. It is a confession that reality has domains where common distance units stop feeling useful. There is another subtlety that makes light years even more fascinating. Because light takes time to travel, there is no single universal now that we can see across great distances. You may think of the galaxy as existing in some synchronized present, but observation does not grant access to that present. It gives us a patchwork of different eras. The Sun as it was 8 minutes ago, Proxima as it was over 4 years ago, the galactic center as it was 26,000 years ago, Andromeda as it was 2.5 million years ago, distant galaxies as they were before Earth had even formed, or when it was still young and lifeless. Astronomy is therefore an odd combination of mapping and archaeology. Every deep image is both a survey and an excavation. We do not just see farther, we see earlier. That is why one of the most famous astronomical images ever taken, the Hubble Deep Field and later Deep Field observations, felt so emotionally powerful to so many people. When telescopes stared at a tiny patch of seemingly empty darkness and found it crowded with galaxies. Not stars in our galaxy, but galaxies, each one containing vast numbers of stars. It was a reminder that empty space is often only empty to limited eyes. And it was also a view into the deep past, because those faint smudges were distant enough that their light had traveled for immense spans of time. To understand a light year fully, you have to hold two truths at once. First, it is simply a unit of distance. Second, because distance and light travel time are connected, it is also a statement about age in what we observe. It is a ruler that behaves like a clock. Now let us ground this again with some examples, because scale only becomes real when it is anchored. Take the Sun. The Sun is about 150 million kilometers from Earth on steams, a distance astronomers call one astronomical unit, or 1 AU. That average Earth-Sun distance is useful inside the solar system, where light years would be awkwardly large. Light takes about 8 minutes and 20 seconds to cross one astronomical unit. If the sun suddenly changed brightness, you would not know immediately. The information would still be in transit. In that sense, even our nearest star is separated from us by a meaningful gap. Take Alpha Centauri, the nearest star system to our own. It's actually a multiple star system. The brightest components, Alpha Centauri A and B, orbit each other, while Proxima Centauri, a dim red dwarf, is the closest of the three to Earth. Proxima is a little over 4.24 light-years away, and that means the light entering your eye from Proxima tonight left before many people had any idea what was about to happen in their own lives over the following 4 years. Starlight always carries this hidden emotional fact. It begins its trip in one human world and arrives in another. Take Polaris, the current North Star. It is hundreds of light years away. Depending on how exactly one measures and models the system, estimates vary, but it is often placed around 430 light years away. So when medieval observers navigated by Polaris, they were looking at light that had left when Europe, Asia, Africa, and the Americas were in very different historical moments than the world we know. The star did not care, of course, but the light stitched those times together. Take the Orion Nebula, a glowing star-forming region, visible as a fuzzy patch in Orion's sword. It is about 1,300 light-years away. The light from that nursery of stars began traveling toward Earth, while human societies were changing in ways no one there could ever know. Yet tonight, if the sky is dark enough, that old light still arrives quietly, turning your eyes into endpoints of an ancient journey. And then there are supernovae. When a massive star explodes, the event can outshine entire galaxies for a time. But we do not witness it when it happens in some universal present. We witness it when its light reaches us. SN 1987, a famous supernova in the Large Magellanic Cloud, became visible from Earth in 1987 because the explosion's light arrived then. The event itself had happened about 168,000 years earlier in terms of local time at the source, because that is roughly how far away the Large Magellanic Cloud is. By the time humans noticed it, the light had already spent longer than our species has spent building civilization on its way through space. Once you start thinking this way, even simple statements become strange. The star is 10 light years away really means its light takes 10 years to get here. This galaxy is 100 million light years away, means we see it as it was 100 million years ago. The universe visible to us is always delayed. The night sky is not live. It is a layered broadcast archive. That idea can feel unsettling at first. We like immediacy. We like to believe that observation gives us the world as it is, but astronomy gently removes that comfort. It tells us that distance creates unavoidable ignorance. There are things happening right now across the cosmos that we will not know about for years, centuries, millions of years, or ever, depending on distance and whether their light can reach us at all. And this is where the story widens beyond stars and into cosmology. Because if light has a finite speed, and the universe has existed for a finite amount of time, then there is a limit to how far we can see. Not because the universe necessarily ends there, but because light from beyond a certain distance has not had time to reach us since the beginning of the cosmic expansion we call the Big Bang. This defines the observable universe. People often hear that the universe is about 13.8 billion years old, and assume the observable universe must therefore have a radius of 13.8 billion light-years. It would be wonderfully simple if that were true. It is not. The reason is that space itself has expanded while the light was traveling. So the most distant regions whose ancient light reaches us today are now much farther away than 13.8 billion light-years. The radius of the observable universe is estimated at around 46 billion light-years. That number sounds impossible the first time you hear it. If nothing can travel faster than light, how can something be 46 billion light-years away in a 13.8 billion-year-old universe? The answer is subtle but crucial. Objects are not necessarily moving through space toward us at superluminal speeds in the usual sense. Rather, the space between us and those distant regions has expanded. General relativity allows space itself to stretch. So the light began its journey when those regions were much closer. But during the billions of years the light was in transit, the universe expanded dramatically. This is why light years remain useful, but must be handled carefully in cosmology. For nearby stars, a light year is straightforward enough. For the deep universe, we need to distinguish between concepts like light travel distance, co-moving distance, and the state of cosmic expansion. Astronomers use several different distance measures depending on what exactly they are describing. This can sound intimidating, but the key idea is simple. In an expanding universe, distance is not one single uncomplicated thing. Still, the basic emotional truth remains. Light years reveal that the universe is not just huge. It is history-rich. Looking farther out means entering older chapters of cosmic time. And those chapters tell us how everything came to be. The earliest universe was not full of stars. After the Big Bang, it was initially hot, dense, and opaque. As it expanded and cooled, atoms eventually formed, allowing light to travel more freely. That ancient light still fills the universe today as the cosmic microwave background, a faint afterglow from when the universe became transparent around 380,000 years after the Big Bang. We do not usually talk about the cosmic microwave background in light years alone, because cosmology complicates the geometry. But the principle is the same. We are receiving ancient radiation that has crossed almost the full age of the universe to reach us. Then came the first stars, the first galaxies, the first generations of cosmic structure. Much of what modern astronomy does is reconstruct this unfolding story by collecting light from different distances and therefore different times. In effect, the universe preserves its own memory in traveling radiation. This creates one of the most beautiful inversions in science. We often think of the distant universe as inaccessible. In one sense, it is. We cannot go there. But because of the speed of light, distance also grants access to the past. Nearby objects show us the recent universe. Distant objects show us the ancient universe. The farther we look, the deeper the archive becomes. There is a reason this feels almost mystical, even when explained clearly. It is a rare case where reality is allowed to keep its poetry after the math is understood. But there is also danger hidden in these distances. Not danger in the sense that a light year is itself threatening. A unit does not harm anyone. The danger lies in what it reveals about isolation and exposure in space. For one thing, space is not empty in the friendly sense. It is empty in the lethal sense. The vast gaps between stars are dark, cold, and thin almost beyond comprehension. There is no air to carry sound, no easy source of fuel, no roadside assistance somewhere past Pluto. Radiation, micrometeoroids, equipment failure, and time itself become brutal enemies. The farther you go, the more unforgiving the universe becomes. And because of light speed delay, help cannot be immediate. Even within our solar system, this matters. Communication with Mars is delayed by several minutes each way, depending on the planet's positions. Our commands to spacecraft near the outer planets can take hours to arrive. Engineers must think ahead. Machines must often operate autonomously. Distance is not just a travel problem. It is a control problem. Now push that to interstellar scales. A crew traveling to a star system a few light years away would leave behind not just Earth, but any practical sense of real-time contact. Their messages would become historical documents before replies arrived. By the time a problem was described and advice returned, years could have passed. A light year turns adventure into separation. This is one reason the search for extraterrestrial intelligence becomes so complicated. If a civilization exists 1,000 light years away and sends a signal, we receive a message from a society as it was 1,000 years ago. If we reply and they answer immediately, another 1,000 years pass before we hear back. Civilizations do not just need to exist. They need to overlap in time, survive long enough, use detectable signals, and be close enough for communication to mean anything within historical timescales. Light years do not merely separate worlds physically. They separate them temporally. And yet, strangely, the same distances that isolate us also connect us. Every atom in your body was forged through cosmic history, shaped by distances measured in light years and more. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, these were built in stars, scattered by stellar winds and explosions, incorporated into clouds, planets, oceans, and living things. The stars are far away now, but the universe is not just out there. It has passed through you. A light year helps us appreciate both truths at once. We are tiny and we are involved. We are local creatures in a non-local universe. There is also an important practical side to all this. Astronomers need ways to measure these immense distances, and light years are only one tool. For nearby stars, one of the classic methods is parallax. As Earth orbits the Sun, nearby stars appear to shift slightly relative to more distant background stars. It is a tiny effect, like holding up a finger and watching it move against the background. When you alternate, which eye is open? The smaller the shift, the farther away the star. This method gives us one of the most direct ways to measure stellar distances. In fact, another commonly used unit, the parsec, comes from parallax. And 1 parsec is the distance at which a star would show a parallax of 1 arcsecond as Earth moves around the Sun. It equals about 3.26 light years. Astronomers often prefer parsecs in technical work because they fit naturally with measurement methods and equations. But for public understanding, light years are often more intuitive because they tie distance to travel time of light, which carries immediate meaning. Then for greater distances, astronomers use standard candles such as Cepheid variable stars or certain types of supernovae, objects whose intrinsic brightness can be estimated. By comparing how bright they appear to how bright they actually are, distance can be inferred. Beyond that, redshift and cosmological models come into play. The ladder of distance measurement grows more complex the farther we reach. But at every rung, the reason we need these techniques is the same. The universe is staggeringly far spread, and because it is so far spread, seeing clearly is hard. Light fades with distance, dust absorbs and scatters it, expansion stretches it. Telescopes must become larger, colder, sharper, more sensitive. Astronomers observe not just in visible light, but in radio, infrared, ultraviolet, X-rays, and gamma rays, because the universe emits across the electromagnetic spectrum. Different wavelengths reveal different structures and processes. Some pierce dust, some expose hot gas, some trace magnetic fields, some reveal violent high-energy events. This matters for understanding light years because not all light reaches us in the way we expect. Some distant objects are invisible in visible light, but glow in infrared. Some are hidden behind interstellar dust. Some are so energetic that their story arrives in X-rays. Looking into the universe is often not looking in the ordinary sense at all. It is decoding incoming radiation from across impossible distances, and those distances can play tricks on perception. For example, when two galaxies appear close together in the sky, they may be interacting neighbors or simply unrelated objects at vastly different distances aligned by chance. A bright star in the foreground can sit visually beside a galaxy millions of light years behind it. The eye sees a near pair. Space says otherwise. Even within our own galaxy, distance changes meaning. The Milky Way is about 100,000 light years across, give or take depending on how one defines its structure. If a civilization lived on the far side of the galactic disk and somehow watched Earth with impossible clarity, they would not see satellites or cities. They would see a planet tens of thousands of years younger. Human civilization in any recognizable form would not yet exist. If they sent a greeting tonight, and if it reached us at all, no human language alive now would survive to hear the reply. That is the true personality of a light year. It is not just huge. It is patient. It does not care about urgency. This also means that many of the things we call current in astronomy are current only relative to received light. A black hole merger detected today by gravitational wave observatories may have occurred hundreds of millions or billions of years ago in the source frame of our observation. A gamma ray burst seen tonight may mark a cataclysm that happened before Earth had forests in their present form. Observation dates are local, and cosmic events are historical arrivals. If that begins to feel disorienting, that is because it should. We evolved to navigate valleys, seasons, weather, prey, and social groups. We did not evolve to intuit finite signal speed over interstellar and intergalactic distance. A light year is where human intuition begins to lose the argument. And yet we can understand it. That is one of the most impressive things about the human mind. We can build concepts that extend us beyond instinct. We can never feel a light year directly the way we feel a room or a street. but we can reason our way into a meaningful encounter with it. Think about how extraordinary that is. A species that started with campfires and naked-eye stars eventually discovered that those stars are suns, measured the speed of light, realized that light takes time, invented a distance unit based on that speed, and used it to map a universe billions of light years deep. There is humility in that story, but there is also quiet triumph. Now, there is a question people sometimes ask when they first really absorb what a light year means. If everything we see is old, can we ever know what the universe is like now? The answer depends on what now means. Locally, yes. We can know our nearby environment with relatively small delay. The moon is just over a second old to us. The sun is 8 minutes old. Mars is a few minutes to tens of minutes away in light travel time. Even the nearest stars are only a few years delayed, which on stellar timescales is practically current. But across the deep universe, no, not in any direct observational sense. Hence, there is no way to receive information instantly from a galaxy a billion light years away. Its now is hidden behind the travel time of light. Yet physics helps us infer some things. If we understand stellar evolution, galactic dynamics, or cosmic expansion, we can model how objects likely changed between the time their light left and the present state they probably occupy now. These are informed reconstructions, not direct live views. Science is often strongest precisely because it can connect limited observations to deeper laws. This is why a light year is not merely a fact to memorize. It is a doorway into how science works. We observe traces. We account for delay. We compare models with evidence. We acknowledge uncertainty where it remains. We build maps from signals that are ancient by the time they arrive. And the more accurately we do that, the stranger the universe becomes. Consider again the stars that seem so ordinary overhead. Many of them are moving rapidly through the galaxy. Some are born in clusters and drift apart. Some are variable and pulse in brightness. Some host planets. Some flare violently. Some have already died and left neutron stars or black holes. But from Earth, they often appear stable, calm, eternal. The light year teaches you not to trust that first impression. What seems fixed may only be slowly changing beyond the tempo of a human life and hidden behind the lag of distance. It also teaches you something about cosmic loneliness and cosmic intimacy. Loneliness because the gulf between star systems is not a poetic emptiness. It is a physical barrier, and if Earth disappeared tonight, the wider galaxy would not know for years, centuries, or longer, depending on where one looked from. The universe does not instantly register our existence. Intimacy, because despite all that distance, light still arrives. The stars touch us with radiation across years, centuries, and millennia. Photons emitted in stellar cores, scattered through atmospheres, redirected by dust, finally end their journeys in telescope mirrors, camera detectors, or the cells of your retina. Distance delays connection, but it does not erase it. This is especially powerful when we think about the history of human astronomy. Ancient observers watched the sky and saw points of light governed by patterns. They could not know what a light year was. They could not know that some stars were hundreds or thousands of light years away, or that the Milky Way was a galaxy among many. But they were already receiving those messages. The photons did not wait for understanding. They arrived anyway. Then came the slow unmasking. Telescopes revealed Jupiter's moons and Saturn's rings. Spectroscopy showed that stars are made of the same kinds of atoms found on Earth. Parallax measured stellar distance. Relativity redefined space and time. Modern detectors expanded vision beyond visible light. Step by step, the night sky transformed from decorative mystery into a deep physical record. And through all of that, the light year remained one of the cleanest translations between human language and cosmic reality. You can almost think of it as the universe forcing honesty on us. Want to talk about the stars? Then talk in terms that respect how far away they are. Or want to imagine reaching them? Then account for the real travel time. Want to know what you are seeing? Then admit that you are seeing the past. There is no cheating a light year. Even in popular speech, the term carries a certain emotional charge. We say that two things are light years apart to mean unimaginably different or distant. The phrase has become metaphor because the underlying reality is already metaphorical in its power. But astronomy gives it back its original force. Light years are not a figure of speech. They are what the universe actually demands. And once that sinks in, familiar things acquire new edges. A sunrise becomes old news from the sun. Planetary exploration becomes delayed conversation. The nearest stars become far-off archives. And the Milky Way becomes a city so vast that crossing it at light speed would take longer than all of recorded human history. Nearby galaxies become visible ancestors. Deep fields become glimpses of a younger cosmos. This can also change how you think about ambition. Humans often ask whether we will spread to the stars, whether our descendants will colonize other systems, whether one day interstellar voyages will become normal. Maybe some version of that future is possible. But if it happens, it will not happen because the distances turned out to be less serious than they seem. It will happen only if intelligence, engineering, energy, patience, and perhaps biology itself are transformed enough to confront what a light year really is. In that sense, a light year is a reality check for dreamers. It does not kill wonder. It disciplines it. At the same time, it offers a different kind of wonder, one less about conquest and more about perception. You do not need to travel across light years to be changed by them. You only need to understand what reaching your eyes has already survived. Every star visible at night is a successful transmission across darkness. Some left before your birth, some before the birth of nations, some before civilization. In a universe where nothing carries information faster than light, every visible object is a delayed act of contact. And perhaps that is why astronomy can feel so emotionally different from other sciences. It deals in things that are both immediate and unreachable. The starlight is here. The star is not. The image is current in your eye. The event is not current in time. You can know the cosmos intimately through measurement and still never stand inside most of what you know. That tension is not a flaw in our understanding. It is the condition of being small in a very large universe. If you really want to feel the scale one more time, imagine reducing everything again. Suppose the Sun and Earth fit inside a neighborhood model. The planets spread out. The Kuiper belt drifts farther. The Oort cloud, if we include it, extends vastly beyond. But even that immense shell of icy bodies, the distant frontier of our solar system, is still only a prelude to the interstellar gulf. The empty space between the Sun and the nearest stars is not full of dramatic scenery. It is mostly dark, sparse, and cold. Light crosses it in years. Human machinery would need ages. And beyond those stars is more of the same. Clusters, and nebulae, spiral arms, galactic halos, neighboring galaxies, galaxy groups, clusters of galaxies, filaments on the largest scales. A universe built from matter, energy, gravity, radiation, and time, arranged across distances so large that our best everyday word for them is still inadequate. So what does a light year actually mean? It means the universe has scale that resists common sense. It means seeing is never instantaneous beyond the smallest human distances. It means every view of the cosmos is delayed, and the farther you look, the older the story. It means the stars are vastly farther apart than the night sky suggests. It means interstellar travel is not merely difficult, but deeply constrained by the laws of physics as we understand them. It means astronomy is an act of reading ancient light, and it means that the darkness above you is not empty of meaning. It is full of arrivals. There is a quiet grandeur in that. The cosmos is not performing for us in real time. It is sending out light in all directions, indifferent, relentless, and often beautiful. Some of it falls on worlds with no one there to notice. Some falls into dust, gas, or black holes. And some, after traveling for years or millions or billions of years, enters a telescope on Earth and becomes understanding. That is a very different picture from the one most of us carry as children, when stars seem like decorative sparks scattered overhead. The truth is colder than that, and more distant, and less comforting in some ways, but it is also far more magnificent. The sky is not close, and it is not simple. It is deep enough that distance becomes time, and time becomes visible. In the end, a light year is a reminder that the universe is under no obligation to fit inside human intuition. We invented the term because our older ways of measuring failed in the face of cosmic reality. We needed a unit honest enough to admit what we had found. A ruler made of speed and patience. A way of saying that space is so vast that even light has to work for it. And maybe that is part of what makes astronomy so moving. The more clearly we measure the universe, the less ordinary it becomes. Precision does not drain away wonder. It sharpens it. A light year is not just a number. It is the moment when mathematics, physics, and human imagination meet the true depth of the dark. So the next time you hear that a star is 4 light years away, or a nebula is 1,000 light years distant, or a galaxy is millions of light years out in the black, do not let the phrase glide by as background language. Hear what it is really saying. That the light took years, centuries, or ages to arrive. That you are looking across distance so extreme, it had to be translated into time. That the sky above you is not a ceiling, but a vast archive of traveling light. And that understanding even one unit of cosmic distance can completely change the way the universe feels. Thank you for being here and for taking the journey.